All right. This is video three. I think this is the last video that we have um in this short. Oh no, we have four. Sorry, my fault. I lied. But the chapter four, I mean the fourth video is like tiny. I may just like run through this one and just squeeze them together. Um so, yeah, now we're going to be talking about long run production. So, long run production has our two variable inputs, right? So, labor and capital are moving. And when both labor and capital are moving, that means that we can now choose how we want to produce a certain level of input, right? Do we want to be labor intensive or do we want to be capital intensive? Do we want to just work everybody a lot or do we want to try to buy a lot of things because that's going to make it the easiest? The production form can be in the form of a Cobb-Douglas function, very, very similar to our utility function, where our A, alpha, and beta are all constants. Again, our exponents are going to be constant. The A is just a multiplier in front. A could very well be 1, and it would just reduce into the normal Cobb-Douglas that we're used to seeing. Um, Almost always A plus B is equal to 1, so sometimes beta is 1 minus alpha. That might be another way that you've seen it. I know we've done an example like that, but for the most part, you'll see it whatever you want, like in lots of different ways. And so now you've got this thing called the production isoquant, which is a very, very fancy word of saying they show the efficient combinations of output that are going to reduce a specific level of, I mean, combinations of inputs that will produce a specific level of output. What does this sound super, super similar to? Indifference curves, right? They are our combinations of two goods, except labor and capital are inputs, not goods that we are going to consume, that will give us a certain level of utility or output, right? So the main differences from the LCs is that they are quantity constant, right? So our Q is always going to remain the same, and they have cardinal properties, which that doesn't really matter for this class. The main properties are further from the origin, the greater the output, just like utility. They can't cross, they can't slope downward, and they must be thin, just like indifference curves. The shape of the isoquant indicates how much a firm can substitute between our inputs, exactly like an indifference curve. And so this big fancy name, production isoquants, is just a fancy way of saying this is our firm indifference curve, and we'll be okay with whatever we decide to do. And so it's got a couple potential shapes. So if we're thinking of two inputs, right, let's say that we're thinking about labor and we're thinking of two different types of labor from skilled and unskilled workers. If we have two functions that 1 hour of skilled labor is going to be the equivalent to 1 hour of unskilled labor, we can just substitute perfectly across the two. Perfect complements. Let's say that we have bus drivers and buses. If we only have a certain amount of buses, the extra bus drivers don't matter. Or if we only have a certain amount of drivers, but we have a lot of buses, we don't have anybody to drive the buses. So they're going to be perfect complements, and we're going to have fixed proportions between the two of them. And then we could also have things like imperfect substitutes. This is going to be what we deal with the most, is some imperfect substitutes, and that is where most of the interesting questions start coming. And so now we've got some substituting inputs with a marginal rate of technical substitution. And the marginal rate of technical substitution is simply just the slope of the isoquant, dq dl. And it is the ability for a firm to replace one input with the other, holding output constant, right? So holding output constant, if we wanted to shift from a labor intensive to a capital intensive, how many hours of labor will we have to put in or give up in order for K for our capital to increase? And a lot of times you can have this written in implicit form and it'll be fine. So if we wanted to calculate the MRTS, right, then so again, the MRTS tells us how many units of K, capital, our firm can replace with an extra unit of L, holding output constant, right? So our dQdL should be equal to 0, right? We don't want our output to change. Output is constant, but it is going to be the implicit function with respect to L times this indirect change here. Or, in other words, the direct change in the marginal product of labor plus the marginal product of capital times the change in capital resulting from a change in labor. And so hence, it's just going to be like given this zero, right? This DKDL is just going to be the negative ratio between the two. What does this look super, super similar to? If we recall, the MRS was minus U1 over U2. It's the same thing. It's just the firm version of the same thing. And so the MRTS diminishes along the convex isoquant. The more labor that a firm has, the harder it is to replace capital with labor. So let's look at an example. Let's find the MRTS. We don't need all of this information, whatever, right? So given L is equal to 97, K is equal to 110, our marginal product of labor is 4, and our marginal product of capital is 6. Well, if we recall, our MRTS is just the negative ratio of labor to capital. So it's going to be minus 2/3. All right, easy peasy. You don't have to think about this all the time. So in the short run, let's consider this as being our uh, let's take back to our previous video. In the short run, we can also find the MRTS, but first, let's find the MPL, right? So we're going to say holding capital constant, right? We're going to get 7K plus 14L minus L squared. Now, holding labor constant, we're going to get 7L, and that's it. And so our MRTS is going to be minus 7K plus 14L minus L squared over 7L. That's it. That's the easy part. That's all you need to do. And remember, this was dq dl. Whoa, that's a bad partial. dl. And this was dq dk. Let's do another example. Why not? Let's just keep doing some examples. So consider a Cobb-Douglas function. We've got alpha is equal to beta. So our output is q is equal to k to the 0.5, L to the 0.5. Let's find the equation for the isoquant. Find isoquant. In order to find the isoquant, we need to have an output that is fixed. So we're going to have 4,000, right? So now we would take this 4,000 should equal k to the 0.5, L to the 0.5. We're going to divide L by both sides by L. And then we are going to get 4,000 over L to the 0.5 should equal k to the 0.5. We're going to square both sides. That's going to be a lot. So we're just going to go 4,000 squared over L should equal k. So this is the equation of the isoquant. If we wanted to find the MRTS, because that's what we've been talking about, we're going to get minus 0.5. And remember, our MRTS is MPL over MPK with a negative out in front. So we're going to get and this is going to simplify into minus k over L. And so now this is why I'm like, I don't think that we're going to need this fourth video. So we're just going to make this video 3B. Let's talk a little bit about return to scale, productivity, and technical change. The marginal return to technical substitution kind of plays into this, but for the most part, we've got these things called returns to scale. So returns to scale is this concept of answering the question of how much does output change if a firm increases all inputs proportionally. Well, with constant returns to scale, a percentage increase in all inputs causes the same percentage increase in outputs. So, for example, doubling our inputs, if we had twice as many hours worked and we had twice as many machines, our output is just going to be two times what it would be normally. Increasing returns to scale says that a percentage increase in all of our inputs causes a larger percent increase in outputs. So, doubling our inputs, twice as many labor and twice as many machines, is going to cause more than two times our original output. And decreasing returns to scale is the analogous thing. A percentage increase in all our inputs causes a lesser percentage. An example, doubling our inputs less than doubles the output. Um, so doubling the wage, doubling the capital is going to be less than if we just worked twice, like 2 years or something. And so there's going to be an easy way that we can look at this, and it's going to be identified using this graph, right? So from C to D, so from here, right? If we move from C to D, there's going to be decreasing returns to scale, right? So we moved from 4 to 8, so we doubled. We moved from 4 to 8, we doubled. From 6 to 8, we didn't. We increased by 2, right? Rather than increasing by 4. Um, From 3 to 6, though, so from B to C, right, we increase by 2, right? We double. 3 to 6 is doubled. So we'll be okay. And from A to B, we have a increasing return to scale. So again, we double here, and this we triple. And so when you're looking at these are called these are the isoquants. Um, That would be the easiest way to identify whether or not you have what type of returns to scale you have. Just look at percent change in outputs compared to percent change in your inputs, right? So your inputs compared to your outputs. And you should be able to figure that one out, whatever, right? And so there's another way that we can think about this a little bit, and we've got this Cobb-Douglas function. With constant returns to scale, alpha plus beta are going to be equal to 1. Increasing returns to scale, alpha plus beta are going to be greater than 1. Decreasing returns to scale, alpha plus beta is going to be less than 1. So you can also identify it from ID from the function. Okay, that's it for chapter 6. Thanks for hanging on. I'm glad that we didn't make that fourth video its own individual video. That thing was super quick. Take a look at the homework, take a look at the quiz. If you guys have any questions, please let me know, and I will see you guys in chapter 7.